CIV4SD3. Today we're going to continue on our lecture examples that we have left. We could not finish that one, double reinforced concrete beam, and now we also going to look at the design of that lecture examples, and then we have workshop examples. So two examples that we're going to cover today, and at the end I will also touch base on the lab activities that you going to take it. So every week with your group members you could be able to complete those lab activity that you needed. Okay, so let's continue on these examples that we left. So yesterday we have on the example number 1. Let me share the screen so you can see what I'm talking about. All right, so yesterday we have done this example so far where we check the reinforcement minimum and maximum reinforcement that we done. Now we just left with the last one that we need to do it, moment capacity of your cross sections. So we just need to find the moment capacity of the beam sections. That moment capacity of the beam sections that we need to find is basically you are taking three components: MU, tension force times the distance, perpendicular distance, then compression force of the concrete times the perpendicular distance DC, and then you have a compression force times DSC, right? So that's the moments equations. If you remember these force one, that you have tension force times this distance D. Then you have concrete compression force, that's distance this DC, right? This is gamma KU D over 2. And then another one, you have a compression force CS and you have this DSC, right? So that's 3 force times perpendicular distance. Now the tension force we have calculated, I think before. The tension force that we have it here, 1808, and this one tension force, this is the force in the concrete, and we have a force 394. This force is in the concrete compression. So we have calculated these three forces that also validate the equilibrium, and we have this distance as well. All these three distance that I mentioned that we calculated, right? The where it was, I think at the start, I think we done D is 520, DSC is 84, and another one is the gamma KUD. That we need to find it out. Okay, so let's I explain you that all the forces and all two distance, and the third distance that we have is this DC. That DC is basically 1/2 gamma dn, and 1/2 this gamma is 0.89, and the dn value is 177 millimeters, right? So in that case we have these 79 millimeters. Now we can substitute all the values. That T force is 1808000 newtons times by this distance is 520. Take away 1414, and I hope all these big numbers that we just find it out before as well. And I know this because from the yesterday, so it's a little bit of discontinuity, but I hope you can crack it by yourself. It's not significantly overcomplicated. The next examples would be little bit require attentions, but this one is just all the forces. And the only critical part is to find these the neutral axis depth, because it required the this interactive process. So so we need to multiply by the capacity factors 5 mu, and if you want to check the 5 mu, let me turn on my document camera so I can show you where you can find the reduction factors. let me turn on the software. So give me a minute, please. It's just turning on this document camera. Yeah, it's on now. All right, so that's you can see. Now, so capacity factors that we want to take it is these capacity factors. If you go back to the start of table 2.2.2 on the standards. Table 2.2.2, you have a capacity factor for bending without axial tension and compressions. You have the capacity factors between these. So basically you take 0.85 when Ku is greater than 0.36. I can show you in my other standards where I have these tables, where I have these graphs as well. Page number 36. So in here I put this graph where you get this one. So if you have this yield strength greater than 0.005 or Ku value is greater than less than 0.36, you have 0.85. Look at this graph. So up to 0.085, Ku less than 0.36, you have 0.80. When you go down, you can do the interpolation. That is basically the interpolations, that equation transition. And from 0.54, or you can have 0.65 onwards, 0.65 onwards, you will have these 0.65 values. So that's what is basically mentions. But here we're going to take 0.85 because our Ku value is 79 kilo, because Ku value is less than 0.36. So you have a 677 kilonewton meter. So that is your answer. Now, so in case if the Ku value is greater than 0.36, what you're going to do it? We're going to increase the ASC. Basically, increase the ASC, meaning when you have this reinforcement, you need to increase the area of this reinforcement. If in case the Ku is greater than 0.36, or increase the depth, increase this depth, this D that you can increase. There are two options that you can. Sometimes architecture don't allow to increase the depth of this one, so only options you have to increase the ASC. Now the next one. By the way, any questions there? Let me try to get the next one. The workshop or lecture 2. Okay, there you go. Now this is a design examples. Design examples meaning, in the previous example was the analysis example. What this analysis example meaning? In that analysis example, ASC given, AST given, and B is given, depth is given, cover is given, the fitment is given, everything was given, and they ask you to find the moment capacity, right? I hope you understand all the reinforcement, the geometric dimensions, and everything was given in the analysis, and then we find the capacity. Okay, now in here, when you have a design of kind of problems, then they give you these design moments, and then you do the reverse. Like here they give you this one, and you need to find the moment. Here they give you moment, and you find this reinforcement, right? So it's a reverse process. That is the design, that you know your moments, that is the design moments coming from bending moment diagrams. Then you need to find the longitudinal reinforcement in the beam sections. Example 1 meaning the same examples, the previous one. The example 1 meaning these examples, that we have this B, D value, everything is given to you. But please remember, in here they have not give you, they have give you 600 by 350 R10 fitment and all the covers and everything given, but the reinforcement has not given to you. Let me copy this one so you know what we are talking about. So let's put it here. Okay, so here you have example number 1 as well. In this one they have not give you this one. You don't know this, and you don't know this, right? So these things are not given, others are given to you. So that's, you need to find it. Okay, that is a design of your example. So let me just get it, my examples in front of me, so I don't make mistakes, and we can get the things done within the given time. So let's say we want to solve these examples. Now, we don't know whether it's a doubly reinforced or singly reinforced, right? Because we don't know that. Okay, if someone give you this beam, is how much was that? 600 by 300. Okay, let's close this one. 600 by 350. Someone said 350 by 600. Okay, and say that okay, you need to put the Rio. We don't know that this Rio will going to work or not. So always you start with singly reinforced. Singly reinforced always. You need to make a checks because we want to do the singly reinforced, right? Eventually we don't want to go because doubly reinforced is expensive. So we want to make a checks whether singly reinforced gonna work or not. So first of all, let's say step number 1, we gonna make it say that check if singly reinforced beam is adequate, right? Let's make it, if it is adequate, then we don't need to worry about it, right? So let's say that we don't need to let's say mu 5 mu for singly reinforced. If you remember, I have that equations that tension force, like if you know the singly reinforced, if you remember the singly reinforced concept where you have this compression force in the concrete, tension force in the steel, and let's say this is Z, right? Lever arm Z. Now, then you have this capacity that you can calculate mu equal to tension force times Z, right? We can take the moment about this point. So this T times Z. Okay, that's fine. T is basically AST, tension force, times by FSY. And the lever arm, that basically 0.85D. Okay, this is just an assumption saying that okay, lever arm generally falls. This is very conservative, but to start with, we want to take a very conservative assumption. So let's say you have 0.85D. This is a lever arm. So basically, depth D is here. So it says that if you have 100 millimeters of depth D, you have this 85 millimeters. That's what it says, right? So it says that okay, you take 85% of your D, that is your lever arm. Okay, that's assumption is saying that Ku is always less than 0.36 for singly reinforced. So that is a valid assumption, very conservative, but to start with is a valid assumption. This is assumption. We're going to verify this assumption, but let's start with this one. So you have 5 and you have AST FSY times 0.85D, right? So in that case, we need to find this AST. Let's find the AST. So let's say mu 5 mu equal to m star, and then you have 5. This mu, let's bring this one across because your 5 mu always greater than m star, right? And let's get this one across. Let's get this one across. Mu greater than m star over 5. Let's say AST FSY 0.85D. This is tension times Z. Lever arm is greater than 5. Right. So in that case, if you want to know what is your AST, then m star over 5 FSY 0.85D. What is your m star? M star was given to us. Example number 2, m star was 639. Okay, so that's fine. Let's put the 639 times by 1000 times by 1000, that is Newton millimeters, over 0.85. You remember that one just in the tables. 500 for n bar megapascals times 0.85. By the way, the D, I think that we're gonna use the same D from our previous examples. If you remember the D from our previous examples, that D we calculated because cover and all these fitments and everything would be same, and the D was here 520. So D was 520. D was 520 millimeters, let's say. So in that case, AST is greater than, if you simplify that's one, you get 3401.65 millimeter square. Now if you go to these Rio tables, if you go back to these Rio tables, and in that Rio tables, if you work it out, N28 3401, so N28 you need 8 bars. You need 8 bars because we have N24, we have 28. Let's say you have N28 bars, and we have a 3696. We need 6 bars, right? Right. So if you go back here, then you need N28 6 bars, and ASD is 3696. ASD equal to 3696 millimeter square, right? So that's your area of steel reinforcement. Now if I want to check whether KU is gonna work it out or not, let me check it out. So if you have a KU, because we need to make sure that KU is less than 0.36, right? That check is very necessary. This check is very important. Why? Because if this check does not goes well, if KU is greater than 0.36, then you have a brittle failure. Brittle failure, right? I show you that in the standards, right? That KU should be 0.36. So if it is not happens, then we need to do the something design differently. So we always make this check in the singly reinforced that KU is less than 0.36. So let me check. How do you gonna find KU? KU is equal to DN over D. DN we don't know, and 520 millimeters, that's for D. Now, if you want to find DN, then you have these equations. Probably you know from the singly reinforced one that just the equilibrium FSY FC dash times by AST on B. Let's find out DN. Alpha 2 value, I think in our last one we have calculated alpha 2 was 0.802, 0.89. 0.802 0.802 times 0.89, FSY 500, and I believe there was 32 megapascals. And ASD we just estimated 3696 millimeter square over B was 350 millimeters. Right. So in that case, sorry, this is not alpha 2 but DN. So this DN, if you work it out, you get 231 millimeters. Now let me check KU. So 231 over 520, you get KU value of 0.44. Ooh, that is not good, because it's become greater than 0.36. If it is greater than 0.36, you can't use singly reinforced. I hope you understand that. That you can design your singly reinforced, that you have 1, 2, 3, 4, 5, 6 and 28 bars. You put it on the tension side, and you can have AST of 3696 millimeters square. But that will increase. This is the strength. Okay, M star is this MU is greater than M star. For this section, 5 MU greater than M star. I'm happy with that one. I'm not strength wise. I'm happy because it has adequate strength to carry this 639 millimeter. But ductility is not good because KU become greater than 0.36. KU should be less than 0.36. Right? So I'm not happy. Why I'm not happy? Because ductility is not there. Ductility check is not passed. The strength check is okay. Strength check is okay, but the ductility did not work out. Why? Because KU is 0.44, which is greater than 0.36. Look at the standard saying that one. Oh, sorry, this is not the one. Somewhere here. Yes, standard is saying that here clause 8.1.5 standard saying section KU greater than 0.36 and all, you need to do this one. Okay, standard does not like it. By the way, standard don't want to design which is greater than 0.36. We always keep it less than 0.36. So so in that case we have an options. What is your options? That you can, because by the way you have this 600 and you have 350, you have two options. Option number one saying you can increase this D, say 100 and 350, and you can keep all this Rio 6 bar and you do all this again. Well, look, the architecture will not like it to keep increasing your depth, right? Because you can think of you have a house, floor to floor height is let's say 3 meters, and then someone said that my structure engineer wants this massive beam here, and then your head will be, you need to bend down every time you go in your room. Well, you not like it, right? So the architecture said, let's say keep it 600. Okay, you keep it 600. You keep it 600. You keep all these depth is 600. Then you have an options that you can throw some bar here and the top, and in the compression side, right? You provide that compression side, but make sure that your KU value is less than, you make all the checks. So we have these options. We have these options, meaning that we will keep the let's say next step number 2, KU is greater than 0.36. We keep the same depth. So we have an option to put compression Rio. What does the compression Rio means? That we going to throw some bar here, put some bar here. Okay, of course tension side we will keep it as well. I will show you in my I have a quick model here. Look, this one. I hope you can see. It's not ideal to show you on the document camera. Is it better to show you on the camera? Let me check whether that will come up with the nice one with the camera. So let's say you want to increase this one. So we need to make some assumptions. Assumptions saying that first primary assumption is we need to have a KU value 0.36, because that's what the troublemaker is, right? That we need to keep it KU equal to 0.36. Now we have 3 options. What is 3 options is? Let's say you have these cross sections, that is 600 by 350, right? And we don't know this Rio. Okay, we just put this Rio here, we put this Rio here. Now in here we have 3 components. What are the components? We have concrete. Let's say put this blue one, concrete. Then we have this bottom Rio. This is the first one. This is second one, and third one is this top Rio. So we have 3 components. So each 3 components will have a moments contributions. So let's start with moment contributions capacity from the concrete. So because please remember we have 639 kilonewton meters is the moment capacity. So each will need to carry some. This will carry, let's say 300. Let's say this one carry 200. Remaining 139 will carry this one. Right? You understand that there are 3 major components, and 3 of them will going to carry individually, right? This concrete will take some, bottom will take some, and top will take. So we need to provide some bottom Rio in a way that it will carry 200, but we don't know whether it's 200 or not, but we will find it out how much the bottom Rio will gonna carry, how much top Rio will gonna. So we will provide the Rio in a way that it will just going to justify that contributions. So we have to find 3 contributions moment wise, and if you add those 3 contributions you will get the final one. So let's say first one that okay, let's say first one is the concrete moment. I hope you understand the story, what we are trying to do. What is the moment contribution? What is the moment contribution for this beam? So moment contributions, if I want to find it out, what is the moment contribution for this case? If you take a value for this one, let's say let me draw it. So this is 600 by 300, and let's put some Rio here. Let's put some Rio here. So if I draw the force only, you have these concrete stresses, and for that concrete stresses you have this force, concrete force, and let's say you have this tension bar, this tension force in the concrete as well. So let's say you have this lever arm Z1. Let's take the moment about these points, right? Let's take the moment about this point. So the moment carried by this moment carried by concrete is equal to this force times the distance Z1. I hope you understand that one. So if I want to calculate the force, then you have, let's say, concrete force first. The concrete force would be the stress times by the area. Now stress is you remember that alpha 2 FC dash, so that's fine. Alpha 2 FC dash. Area is if you remember this gamma KUD, so that is the height of that gamma KUD times by this B, width B, so that's the area, right? So alpha 2 was 0.802. If you remember that from our previous examples, that we calculated alpha 2 0.802, FC dash 32 megapascals, gamma is 0.89, where it is 0.89, we calculated. Ku was 0.36, where was that? Ku, that we make an assumption saying that Ku should be 0.36 because that's what we wanted, right? D is 520 millimeters, where it is D is 520, that we calculated, and then you have B 350 millimeters, that B that we have given in the examples, right? 3B. Now if you work it out this one, let me work it out this one. 0.802 times by 32 times by 0.89 times by 0.36 times by 520 times by 350. So you get massive number 1496539.7 Newton millimeters. Oh, sorry, just a Newton. So you will have 1496 kilonewtons, right? Or you can put 1497 kilonewtons, right? So that is the force carried by the concrete. And what with the moment carried by the concrete? Moment, let's take MU1. Let's say, let's give the name. That moment carried by the concrete is MU1, which is the force times distance Z1. The force is 1497 kilonewtons times by the distance Z1. So by the way, this Z1 you can calculate by taking this D, which is 520. That sounds good. 520 millimeters. Take away this distance, half of this gamma KUD. Gamma KUD half. So 520 take away gamma is 0.89, KU 0.36, D 520 over 2. So if you simplify that, you will get 0.89 times by 0.36 times by 520 divided by 2. You get 83 millimeters. 83, so 520 take away 83, you get 437 millimeters. 437 millimeters. Now you just plug that 437 millimeters, let's say divide by thousands to get it into the meters. So you have 1497 times by 437 divided by 1000, you get 654 kilonewtons meters. Right, so 654 kilonewtons meters, you have moment. What is this moment? mu1. By the way, this moment 654 kilonewton per meters is carried by the concrete. The moment carried by concrete is equal to 654 kilonewton meters, right? So that is mu1. So the first one done, that we have a as I mentioned, we have three components, right? We have three components that we need to look for. That we have a concrete, we have a compression reo, which is top reo, and we have bottom reo, which is a tension reo. So the first one done, that if someone asks what would be the moment carried by the concrete, is 654 kilonewton per kilonewton meters. So that is the moment carried by the, I hope you don't have any problems to calculate this moment carried by the concrete, right? If you forget about the whole examples, if you someone asks, can you tell me how much moment would be taken by the concrete? Okay, so that is just a force times perpendicular distance, and we take the moment about this tension force, and then you have mu1 equal to 654 kilonewton meters. So that is the step number one. Of course, step number one was we find it out whether the singly reinforced is adequate or not. The strength wise it was okay, but you can use 6 and 28 bars with 3696, that it will have enough capacity. But Ku was greater than 0.36, so ductility was a brittle failure, and we don't, the Australian standard don't allow to have a brittle failure. So you want to have a 0.36 or less. So in that case, we said, okay, no problem. The depth is not allowed. We only have an options to make it doubly reinforced concrete beam by putting the reinforcement on the compression side. So that's what we done. In that doubly reinforced, we take Ku equal to 0.36 because that's what we wanted in the doubly reinforced concrete beam. So we don't know those reos, so we started with the concrete, saying that concrete has some moment capacity. So if you just wants to find the concrete as a moment capacity, just force in the concrete times by the lever arm, taking the moment at tension bar, and then you will have this concrete moment capacity carried by the concrete. Now, second one is what would be the moment carried by the compression reo. Right? This is second one, that we want to know how much moment would be carried by this top reo, because we know how much this concrete is taking. Now the next step is how much this top reo will gonna take it, right? So how much it's gonna take it, because as you know that let's say 5, this is, let's say, concrete one, let's say this is top reo one, is equal to m star. Do you everyone agree with this one? That this is a reduction factors, this is the moment carried by the concrete, and this is the moment carried by top reo. You might ask what happens to the bottom reo. It will come, but let's work it out that you have only two brothers, that you have concrete and you have only steels. Okay, so let's say these are at that you have a concrete one, that mu1, we will add one by one. So let's say you have only two components at the moment, we will add one by one those components. So saying that, okay, you have a concrete, you have this concrete capacity of the moment, and you have this top reo moment. If you add them together, they will give you total 639 kilonewton meters. 639 or 693, what was that? 639, I believe. 639, yep. So it says that, okay, if you add those two guys, then you will have this capacity. So I know this is 0.85 because 0. and this one mu1 for concrete was 654 kilonewton meters, plus mu2 is the top Rio, and this is 639 kilonewton meters, right? So in that case, if I want to calculate mu2, we will get 639 over 0.85, take away 654. So mu2 would be 639 divided by 0.85, take away 654. So it will have a value of 98 kilonewton meters, right? So what would happen here? That happens here saying that, okay, the concrete will going to carry the top Rio will going to carry 98 kilonewton meter this force. So what happening here, that we need to put the Rio, that okay, this concrete, you need to put the Rio in here, which has a capacity of 98 kilonewton meters, right? So how much reinforcement required at the top, that will be enough to carry 98 kilonewton meters. Sounds good, there is no any issue. So if I draw again this force diagram, and this time I'm just going to put these concrete ones, that I'm just going to put these guys only, that you have CS. CS is the compression force taken by the top Rio, just this one. And let's say you put this tension bar here as well, so you have this tension bar here. Concrete one I'm not putting it, because there was a concrete one here, that I'm not putting it because it will just create a conjunction for me. So in that case, let's take the moment again here, the same point that we done it in the last times, and let's give this lever arm value Z2. Right? I hope you understand that we take the moment again and we work it out. So mu2, which is the moment carried by this 98 kilonewton meter, is the force times by the lever arm. I hope you understand that. Right? The moment carried by this top Rio is 98 kilonewton meter. This moment equal to force times perpendicular distance. Force in the top Rio is CS and lever arm is Z. Now lever arm Z, let's calculate this lever arm. So probably if you remember the positions, the position of the top Rio is from the previous examples, we have calculated this DSC, I believe somewhere here, that is 84. If you remember that DSC was 84, top Rio distance 84. I think you remember that from the top cover and bottom cover. This cover basically does not change in the design, okay, they stay as it is. So we know that this distance is 84 millimeters, and we know that this distance D is 520 millimeters, right? So if I want to calculate Z2 is basically 520 millimeters, take away 84 millimeters, I would have 520 take away 84, you get 436 millimeters. So if I want to calculate the force taken by this top Rio, then mu2 over Z2, this mu2 was 98, let's multiply by thousands, you get Newton into millimeters, over Z2 is 436 millimeters. So in that case, you would have a force 98 divided by 436 times by 1000 times by 1000, you get 224,770.6 newtons. So 225 kilonewtons. Let's say the force taken by these top Rio is 225. So if you know the force, by the way, if you know the force, then you can calculate the area required by that one. So, but look, this top Rio need to be yielded and so on, because it's very close. You remember from yesterday, this top Rio that may not be yielded, right? We need to check that this top Rio, if you put it here, and if you draw the strain diagram, if you draw the, let's say this is bottom Rio, if you draw the strain diagrams, this strain here is very close to this DN, so it's, let's say ESC, okay. strain in that one. So let's calculate this strain in that, because this is 0.003, and let's say this is dn, right? So let's take this triangle, the small one, and this height, uh, uh, and this is DSC. This distance would be dn minus DSC. So ESC, strain, over dn minus DSC, right? This is DSC, is equal to 0.03 over dn. I hope you understand that these two triangles. I can draw it up neatly here, that this distance is dn, this strain is ESC, and this distance is DSC. And if I want to calculate this distance, that would be dn minus DSC. So if I use this triangle, I can make it this one. And if I use this big triangle, I can make this horizontal distance, which is 0.03 concrete strain over vertical distance, this horizontal distance over vertical distance, this horizontal distance equal to this vertical distance. So I want to find this ESC. ESC equal to 0.03 times by dn minus DSC over dn. Right, so we need to calculate this dn because we have all the values. So basically dn can be calculated from Ku. Ku is equal to, let me check what happened. Alright, so that's all good. So Ku is equal to dn over d, right? So Ku was 0.36 if you remember from the last one. Dn was d was 520. So dn you can calculate 520 times 0.36. So 520 times 0.36, you get 187 millimeters. So let's plug that value. 187, DSC was 84 over 187, right? 84 was here, 84. So if I just simplify that, you might get the value saying that saying that this will be 0.0017. 0.017. Now, then you need to calculate the stress in the top bar. Stress in top bar, we have a sigma SC is equal to strain times Young modulus. So that would be 0.017 times 200,000. That is the Young modulus. So we have a, let's say, 331 megapascals is a stress. Now once you know the stress, you can find the area, right? Because stress is equal to force over area, ASC, and we need to find that ASC. So if I want to find ASC, we can have a force over sigma SC, and the force, I think we got the force somewhere. Yeah, here you go, force 225. So we have a force which is 225 times 1000 to get it in the newtons over 331. So you get 225 times 1000 divided by 331. You get you get around 680 millimeter square. Right. So if you get 680 millimeter square, go back to here. Here 680. How much was that? 680. So if you go back here 680, you could provide either this one. You can see if you have N28 bars. By the way, let's check it out. What was the assumptions in our top bars? So the top bar assumptions was, how much was that? N28 bars. Yes. So sorry. So N28 bars, and we could put these 1, 2, 3, 2 with the 2 bars. is 1232. By the way, this looks like a too much over to me, because you can look that one, that we could, because we have assumption of n28 bars. Okay, how many n28 bars? We could put 2 n28 bars. There is no any issue. And we have ASC of 1232. So it's quite high. 123, almost double. Right, we have put extra because it's costly to have a 2 n28 bars. Instead of doing that one, we might end up using these 24 bar size and 904 by 2 bars. Okay, someone might argue that okay, we need to go back and check again. Yes, of course you need to go back and check again, because you want to save some money for your client. So we might use 2 n24 with ASC of 904. That could work. 904 millimeter square, right? So probably we can adopt this one. We can adopt this one for economic purpose, for cost saving, right? Because look at the difference, right? You have 1, 2, 3, 2. You have 28 bars, huge bars, and it will end up with 1, 2, 3, 2. Which is quite larger than 608 millimeter square, 680 millimeter square, which is requirement, right? So well, in the exams there is no any issue for that one, but for your practice you might want to reduce that bar to 904 millimeter square, to making sure that you have enough. So I hope you understand the story so far, what we are trying to do. What we have done, that we have given, I can just summarize in the 2 minutes, that we have given these problems. In these problems, they say that you have these moments 639 that you need to satisfy, and you have everything meaning that you have this 350, you have this 600. By the way, saying that you can't increase this one. Okay, you can't increase this one. You need to keep this 600 as it is, because the architectures don't want to increase that one. Now it says that you don't know this Rio. You don't know this Rio, but you can say that there is a n28 bars on top and bottom. That's just to start with, that you want to use n28 bars top and bottom. And the concrete compressive strength is 32. The bottom cover is 30 and top cover is 60. That was given to you. Now we want to, let's say we don't, because we don't know, let's say we want to put this one or not. So let's say we start with only putting the bottom bars, because 639, if you end up with using bottom bar, then it's a winning point for us, because singly reinforced. So we said okay, let's check for singly reinforced. Then we quickly done a very crude one. They're saying that okay, the capacity of the singly reinforced is tension force times the lever arm 0.85 D. And we said okay, approximate AST you need is 3401 millimeter square. And it says that okay, to based on this one we can provide 6 and 28 bars, which is 3696 millimeter square. Sounds good, but this 3696 it looks okay. There is no any issue for that. Strength wise is okay, that is enough. But when I check KU to calculate DN, it's just greater than 0.36. It's quite greater than 0.44. Then we can't use it, right? We can't use this one because of the ductility purpose. So this 3696 is not allowed. That you can't use only tension. So, and this depth is not increased. We could increase this 600 to 700, and we could make it KU less than 0.36. We can keep increasing the depth, but the depth is not allowed. Then only option is to put the compression bar, right? We have a compression bar. So we don't know now that how much compression bar we're going to put and how much tension bar we're going to put. But we know that we're going to use N28 bars. We know the how much cover that we have. We know the fitments as well. Now for that, as I mentioned, I divided into 3 components and take KU equal to 0.36. Let's say there is nothing. We just want to make it concrete. The whole structure is concrete. There is no bottom Rio. There is no top Rio. Just a concrete. Just a block of concrete. That's just one block of concrete, which is 350 by quick block of concrete and 650, how much moment will be taken by, let's say, mu1? How much moment will be taken by mu1? So that we calculated by just saying force times distance and so on, and we calculated this is the moment carried by this block of concrete, 600 by 350. Now 654, that sounds good, but then we throw some top Rio, right? But we don't know how many. We're going to use N28 bars. Based on that, we will say that okay, let's put the top Rio, then you put plus concrete and you plus top Rio, and then that's the capacity for 639. And then you find it out how much moment will be taken by the top Rio, right? That okay, you will take 98. Now if you take a 98 and then if you just do the force times distance and you calculate the force and then you calculate the stress from the strain and then you calculate the area, that's 680. Then you will find that okay, 2 bars is enough for 28, which has 130, which is quite large, so we just end up by using 2 and 24 bars. So I hope you understand that so far. Now saying that we want to know how much, because we done this one now so far, that we're going to have a tension bar which is 2 and 24 bars, we're going to put it there. And we need to question is how many we're going to put it down here, and we have N28 or N24 bars, so we have these provisions here, right? N28. So let's say we want to have a tension force taken by the steel. So we have so far here the force in the steel, force in the concrete, and we have a force in the tension bar. So if I want to have a force equilibrium, now I am working for these guys. Okay, let's say force equilibrium, tension force equal to compression force. I hope you understand that, or you can say that tension take away CS minus CC equal to 0. All the force sum. This is positive force, this is negative force, this is negative force, or force equilibrium, because you need to have a, this is moment equilibrium is okay, but we need to have a force equilibrium as well, right? You can't have one force going in the one direction more than the other one, so we need to have that equilibrium as well. Saying that okay, we can substitute the value CS. I think we know force carried by this one was 225 kilonewtons, so that's fine. 225 kilonewtons force carried by the top bar, and the force carried by the concrete, we calculated that somewhere, let me check. Oh yes, force carried by the concrete was 1497. So let's put 1497. So 1497 kilonewtons. Let's add them together. 225 plus 1497. You get 1722 kilonewtons is carried by the bottom Rio. So if I want to calculate force is equal to area times by the stress. Because bottom bar is at yield, right? Generally the bottom bar at yield, top bar not yielded. Therefore we because from my previous experience we know that this is the scenario. So we know 1722 times 1000 newtons tension, AST we don't know, and 500 megapascals we know. So AST we could put 1722 divided by 500 times by 1000, so you have 344 millimeter square. In that case, let's go back. Let's go back here. Now, please note we changed this we change our bars. We change our bars. Let me go back. Do you remember that we changed these bars here to N24? We're not using N28. Of course, our initial assumption was 28. But look, we don't want to order two different set of bars. So if you put N24 top, I also encourage you to put N24. But of course, if you, for the calculation purpose, if you want to use this one, you can use 3444. So you can use this one. That N, you have option of using N28, sorry, 6 bars, and you have AST of of 3696 millimeter square, which is greater than your required 344. So that is okay. But we don't want to order two different set of bars. It is difficult for these persons to look, oh, top bar 24, bottom bar 28. It's create labor cost increase. So in that case, let's stick with 24 at bottom and top. It looks cost effective, and we could go for this 3616 and 28 and this one. So we have an option of using 8 and 24 bar with the AST of 3616 millimeter square. Again, is greater than 344 millimeter square. So I hope it is okay now that we have these two bars, which is 2 and 24, and we have 8 bars. So we can't use 8 bars in the one go, so we can use 4 bars, and then we use spacer bars, and we can use another 4 at the top, so it will become 8 and 24. Okay, so that's the answers now. And of course, if you want to check again all these analysis performed, KU less than 0.36 for new cases, all these minimum moment requirement and all, you can perform it in the real world situations. But I hope you understand that. Let me know if you have any questions. I was talking for 1 hour. I'll repeat again what I have talked about. Okay, so I think this is the, let me close it off this one. So we have a first principles, determining the theoretical moment capacity, MUO. So we need to find this MUO. And we have a 800 by 450. So we have 800 by 450, depth is 800, width is 450, and they told us we need to do the analysis on doubly reinforced with FC dash equal to 32 megapascals and 40 millimeter cover and R10 stirrup. Okay, so, and as I mentioned, if the cover is not given to you, you can, I think in the week number somewhere 2, where we have taken some examples how you're going to specify the cover. Stirrups R10, that is for sear, and we have 2 layer of 6 and 24 bars. So you have total 12 and 24 bars and N32 spacers. Top Rio is as well 6 and 24, 4 and 24s. So we have these details. I think you know the drills by now, that you need to have this nice figure drawn for you, that you can just draw it big, and then you have these 4 and 24s. Let me write it here, 4 and 24s, and then you have this again 1 2 3 4 5 6, and then you have another 1 2 3 4 5 6, and then you have this spacer bar, and then you have this Rio as well. Right, so that's the story. Now you have this distance 800 millimeters. You have this distance 450 millimeters that is given to us, and now the position is 40 covers everywhere. I think everywhere the 40 covers. So you have cover 40 here, you have 40 millimeter cover here, and you have 40 millimeter cover here. Alright, so we have this one. So I think you know that drill, that you need to calculate this distance. For any reasons you need this distance for that purpose, and we need this distance as well, that is small d, right? So you for any calculations we need those. For any beam one, you need this one, small d you need it. If it is doubly reinforced, you need DSC, you need alpha 2, you need gamma. Those are just by default. You need DN, you need KU, you need AST minimum, you need minimum moments. Those are the typical recipes for the beams. Okay, you can't do without those things. Okay, is must. you don't have any examples where you don't have alpha to gamma or dn or so on, or ku and so on. So you for any beam calculations, you want to know all these parameters, that how the ds, you close your eyes and you need to get these details anyhow, and then later on you're gonna use it one by one, but those details you need it for any reasons, if it's singly or doubly. For singly reason you don't need this one, but for doubly one you need this these parameters. So let's crack it. Small d, that would be 800 millimeters, this one. Then take away 40 millimeters, take away these fitments. Fitment is 10 millimeters, fitment is 10 millimeters. Take away this diameter of the bar, bottom bar was 24, so take away 24 millimeters, and this spacer bar is 32, so we need to get 16 here, so we get 16 millimeters. So I hope you understand that. So 800, take away 40, take away 10, take away this 24, and take away this half distance. If I draw it big, this is spacer bar, this one is Rio. There are 6 of them. 1 2 3 4 1 2 3 4 5. Let's put 6 one. Then you have these parts, and you have this one is 40, this one is 10, this one is 24, this one is 16, because you have 16 here, 32. So oops, sorry. So that is 16 and 16 here. So if this is 800 from top to here, so then if I want to find out from here to here, you can take 800, take away 40. By the way, from here, 800, take away 40, take away 10, take away 24, take away 16. I hope you understand that, right? So if you just use the calculators, you will end up taking 710 millimeters as a depth. DSC is here. So let me calculate DSC is equal to this 40 millimeters plus this is 10. This fitment is 10 millimeters plus this half a distance of 24 divided by 2, so 12 millimeters. So DSC 40 plus 10 plus 12, you get 62 millimeters. Right? So these two details are must. D equal to 710 millimeters, and you have a DSC 62 millimeters. Okay, so let's put it in the box, because we know we need those details. Another one is alpha 2. I think you know the drill now. Alpha 2 is equal to 0.85, take away 0.0015. FC dash is 32. So by heart I know this one 0.802 greater than 0.67, so therefore it is okay, and the gamma value is 0.97. 0.97, take away 0.0025 times 32, you got 0.89, which is greater than 0.67, therefore it is okay. I will show you for the completeness that D equal to 710 millimeter, DSC is 62 millimeter, alpha 2 is 0.802, gamma is 0.89, right? So that's here where it is. I think, and by the way, for your purpose, you work it out these two. This is a bending one. This is a bending one, and then you need to use this table 2.2 as well. This table 2.2 for capacity factors, 0.85 when you have Ku less than 0.36. So this is, I'm talking about alpha 2 and gamma. In clause 8.1.3, 0.85 take away 0.015 FC dash, and gamma value 0.97 take away 0.025 FCDS. Make sure it's greater than 0.67. If it is less than points, you take it 0.67. All right, so that's those recipe that, as I mentioned, is required for that case. Now let's make an assumption that ASC as it yield. So we have those bars, right? Like in the lecture examples. Do you remember in the lectures examples what we done? Step number 1, we obtain DSC alpha 2 gamma. They are easy done, right? There is not any issue, right? That is just you take this one regardless of any examples, that you know you need those 3-4 parameters regardless of whatever the example. So once you done that one, in the step number 2 for the analysis, we assume that top Rio at yield, okay, and we find DN. If you remember that yesterday, right? That we done DN. We find that DN value, some value. And then step number 3, we're going to check if top Rio is yielded or not, right? After finding DN, using this DN, let me put using DN, we're going to check for that particular DN is top Rio is yielded or not, because we have this assumption. Now if it is not yielded, basically it will not yield because it's very close to the DN value. So if it's not yielded, we need to iterate to find DN. Right? You remember that iterative process, that you need to keep adjusting the DN value until you get the equilibrium, force equilibrium, until you get the force equilibrium. Right? So that's the step number 4. Once you get the force equilibrium, then we good. We good means we need to check for ductility. Now you know the drill now, that how we going to check for ductility. Check for ductility would be Ku less than 0.36, or we will check the reinforcement less than maximum reinforcement. That's also we can do. So one of those check will give you ductility checks. Once everything is okay, we just going to check against the minimum. Let's say this reinforcement minimum of actual reinforcement of P maximum. That's conditions we're going to check. Once everything is okay, finally we're going to calculate moment capacity, calculate MUO. So I hope you understand that we just obtain those 4 basic parameters, then we assume that top Rio as at yield, and we said okay, find the DN. Just find the DN, that so we know what is the DN value, that what DN value we're going to start with. Then once you know roughly where the DN going to sit when the Rio is yielded, then we can start iterative the process until you get the force equilibrium. And then once you have force equilibrium, then ductility is very important, as you know, that Ku should be less than 0.36. If it's not, then you increase the depth or put those reinforcement increase on the compression side and so on, and then we calculate MUO. So let's start using it. So as you know, first step is done. Now we want to do the second step, that is we assume that Rio as at L and we find DN. So let's say step 2, let's say top Rio is at yield point, okay, and that is the assumptions, and we're going to check later. For these assumptions, okay. Now if I say that top Rio is at the yield, then the force in the top Rio is equal to yield strength in the top Rio times by the area in the top Rio. So if it is at yield, then we can say 500 megapascals yield strength times by the top Rio ASC. By the way, in this one, we need to find these parameters. Just add this on ASC and AST. Okay, so let's put this ASC and AST as well. What was that? ASC 4 and 24. So ASC 4 and 24. Go back to this. Yep, 4 and 24. So 24 4 bar 1808. So 1808 millimeter square. And AST equal to how many bars you got? AST you got 12 bars, I believe. 6 bottom, 12 bars total. 12 and 24. So you have 12 and 24. You got we don't have 12, so that's okay. We can take 6 and then double it. 2712 24. So that's fine. 2712 millimeter square plus 2712 millimeter square. So because that is for 5424 millimeter square. Right, so I hope you understand that. 6 bar 6 bar, so total 12 5424. So now you have ASC, which is we calculated 1808 millimeter square. Now we will have 500 times 1808, you get 904,000 newtons. So that is your force in the top Rio. Force in the concrete, alpha 2 FC dash times area gamma Ku gamma B dN, because you have Ku we don't know. So let's say 0.802, we calculate this 32 megapascals times by 0.89. B is 450 and we don't know this dN. So in that case, you can take it 10,278.4 dN newtons. And the force in the bottom Rio is tension force is equal to, let's say bottom Rio is also at yield 54, how much was that? 5424 I believe. Yeah, 5424 area millimeter square times by these 500 megapascals is basically Newton per millimeter square. So in that case, you would take it 2712000 newtons. Right, so you have all these forces. Now equilibrium, you know this equilibrium that you have these 4 and 28 bar and you have these 1 2 3 4 5 6 1 2 3 4 5 6. So the equilibrium is this force has, let's say, CS, you have a concrete one CC, and you have this tension force. So all the forces acting horizontally should be in equilibrium, not the one force going in the one direction is more than the another one. So let's say tension force is positive, CS negative, CC negative, equal to 0, right? Because that is the equilibrium. Now if I use tension force, then 2712000 newtons, this tension force, take away CS is 904,000 Newton, and this CC is 10278.4 dN equal to 0. So if you simplify that by using the value dN equal to 176 millimeters. Right, so that is the dN value that we calculated, depth of the neutral axis. By the way, depth of the neutral axis meaning that you have these 1 2 3 4 5 6 1 2 3 4 5 6 and then you have 1, 2, 3, 4. So if you just draw this strain profile, then you have this dn value, that is 176 millimeters. For that 176 millimeter, that top Rio should be at yield. ESC should be at yield, meaning that ESC should be greater than yield strength. Okay, so the yield strength, if I want to calculate for any bar, is 500 megapascals, which is the yield strength over the Young modulus of your Rio. So that will be 0.0025. So the strain in the top Rio should be greater than 0.0025 to make the validation of this dn equal to 176. So if the top Rio is greater than 0.0025, that is fine. There is no any issue for us to go and change any parameters, because if it's not yielded, then we can't use this 500. If it's not yielded, we need to use this less for this top Rio. So then we need to do the iterative process. So let's check. Let's check that. Okay, we can use this. We can use this 176, and you know this is DSC. This is DSC, and this distance from here to here would be DN take away DSC. So if I use these two triangles, one is the smaller one, which is ESC, and this is DN take away DSC. I draw this one, okay, draw this one, and this big one is, let's say, 0.003, and this depth is DN. So similar triangle, horizontal distance over this vertical distance is equal to horizontal distance over this vertical distance dn. So if I want to calculate the strain, 0.003 times dn minus dsc over dn. So let's plug the values. dn for that case is 176 millimeters. Take away DSC. Remember that DSC that I mentioned, you need those DSC values is 62 millimeters. 62 millimeters over 176 millimeters. So in that case, if you work it out, that would be your 0.0, just give a minute for that to 0.0019. Okay, so let's check. What is the check? That ESC, which is 0.0019, is less than ESY, which is 0.0025. So top Rio is not yielded, which is not good. Not good meaning that we need to do the dn iteration process. Calculate dn, calculate or find the dn until you get this equal to 0, this t minus cs minus cs, t minus cs minus cc equal to 0. So we started dn equal to 176 millimeters. 176 millimeters, and it did not work. Right, so we need to try some dn value in a way that we're going to make sure that we have an equilibrium values. So for that, let's try dn equal to 200 millimeters. Now if you try dn equal to 200 millimeters, then you calculate the strain again. You know this drill, right? You need to go for these equilibriums over and over. So let's change this value, that you have a 200 take away 62 over 62. What I done, I'm just making the changes here. This one dn, I'm just making the change, which is 200. So you get strain to stress and then force, right? That's the procedures that we're going to follow. So 0.0021. Okay, close to 0.025, but still it's not yielded. So stress in the top rear is 0.021 times the Young modulus. You will get 414 megapascals. So the force CS equal to area times by the 414. You get 748,512 newtons. Similarly, you will get the concrete one, because concrete one also there, alpha 2 FC dash, alpha 2 FC dash 32, and the area was 0.89 times by the DN times by the 450. Basically, I'm just repeating this one. I'm repeating this whole process. All these equations are same. The only difference that I get is this, because you get new value for this one. This difference, that's it. Two difference that I do, and then I continue checking whether this equation equal to 0 or not. I hope you understand that. Therefore, I'm not writing those equations again to save some time. So you have a 20. Let me put this one in the kilonewtons, so that makes 749 kilonewtons. 749 kilonewton is just divide by 1000. So, okay, if you get the big number in the calculator, you can just put it 2056 kilonewton. Just divide by 1000 to write it easy. And the tension force does not change because it's not depend on 2712 kilonewtons. The same one that we done the last one there, the 2712, there will be same. So if I check the equilibrium, I would have a CC plus CS minus T equal to 0. So you just do this 749 CC plus 2056 minus 2712. You will get around 92 kilonewtons, which is not 0. So 200 did not work out, right? 760 would not work it out. Now you remember that if you go on negative side, then it would be good. So let's go down, right? Because this will give you positive, this will almost 0. So let's try dn equal to 190 millimeters. Now if you try 190 and try again here, that let's try here itself, let's change it to this one, 190, and if you change and use the calculators, you get 0.00 these ones, or 0.002. So if you have a 0.002, then you will get around 404 megapascals. So that is 404 megapascals. Just change the numbers. Then you have a 1808, that is the area, times these 404. So you will get 731. So 731 Newton, 731 kilonewtons. Right, and here we have to change 200 instead of 190, right? That's the change. And if you do that one, you will get 1953. You get 1953 kilonewtons. So let's try again. 1953, 731, and this will not change, and that value you will get is negative 28. So let's keep it here, that 200 dn, you get 92 kilonewtons as a force equilibrium residuals. And then you have dn 190, you will get, this value would be minus 28. So then you get minus 28 kilonewtons. So how much dn that you needed to make it 0 kilonewtons, right? So you can do the interpolations. 190 millimeters over 200 millimeters equal to minus 28 minus 92 equal to, you can say x, take away 200 over 0 take away 92. So if you just simplify that as a DN value, you will get 192 millimeters, very close to that values. Now we can try again. Try again meaning that let's put the 192 here. Let's put 192. Let's put 192 here. 192. You will get 0.02 again, 0.02 again, 404. You get 735 on all because I think 731 still works. So and if you do this one 192, you might change this one to 1977. So 1977, and this will stay as it is. So you have 1977 plus 731, just rounding error, okay, but you can work it out. That would be almost minus 0.5 kilonewtons. So it's almost 0, which is equal to 0. So we can add up 192 millimeters. We can add up 192 millimeters. That will just give us the equilibrium of this strand. So I think 192 dn is okay now. Now this is the strand that we done the strand dn. Now we need to do the ductility check. Ductility check. We can have a couple of ductility checks. We can make it. How are we going to make a ductility checks? Ku should be less than 0.36. This is the option number 1. If I want to calculate Ku, you have dn over d. dn would be your 192 millimeters, and d, I think you remember in the step number 1, we always handy those numbers. 710, I believe. Yep, 710. So 710 millimeters. So 192 divided by 710, you get 0.27. So less than 0.36, therefore it's okay. Ductility check is okay. The beam size and Rio numbers or area of Rio are adequate for ductility requirement of AS3600. And you know the drills. If Ku is greater than 0.36, you would increase ASC or depth, right? Remember in the first examples we done double reinforcement. So this one is lucky, that's done. Now the second checks we're going to make it is that this P minimum is greater than our actual Rio is greater than less than P maximum. So that's checks we're going to make it. Okay, let's calculate those one by one. So let's say reinforcement ratio P equal to your AST take away ASC over BD. Now how much AST? We have 5424 millimeter square, take away 1808 millimeter square over B, 450 times D is 710. You can find this ratio as 0.001. Right, that is okay. Let's calculate this Rio minimum. How are you going to calculate the Rio minimum? This one Rio minimum. This is AST minimum. So if you bring this B and D across, that become minimum reinforcement, because this is the minimum area of the reinforcement in clause number 8.1.61. So AST, B and D, bring it across. You can write alpha B. Alpha B is 0.2. You can check it here, alpha B for rectangular section 0.2. So I can write that rho, because you can see rho is AS2 over BA2. So I can write this rho is greater than or equal to alpha B D on D square FCT dot F over square root Fy. So let's say rho minimum. Oh, sorry. Basically, this AST on BD as a this minimum reinforcement greater than or equal to 0.2 from the standards. I am writing it times D on small d square times FCT dot F dash over FSY. Now in here, FCT dot F dash is equal to 0.6 times square root 32. Where is coming from? I think you know this one. If you go back to the section 3, if you go back to the section number 3, here you go, section number 3, clause 3.1.13 tensile reinforcement, FCT dot F is equal to 0.6 square root 32. FCT is square root 32. So you will get this one as a 3.4 megapascals. So we can plug this value that minimum reinforcement required according to the standard is 0.20. Depth of your section is 800 over 710 square. FCT just we calculated 3.4 over 500. So minimum reinforcement, if you work it out, you will get 0.002. Okay, so that sounds good. What is this one? Is standard saying that look guys, you need to provide the minimum reinforcement in your steel beams regardless of your demand. Meaning, some might say, smart engineers come back here and say that, okay, I just want concrete only. Let's say 800 by, sorry, what is the 800 by 450, I believe? 800 by 450. 450, right? Yes, 450. Okay, so some smart structure engineers come back and say, let's save some cost. Why we buy the steel Rio? Let's have a concrete only. Let's make the beam out of concrete. Why? Because I satisfy the capacity, saying that your demand, let's say you have 500 megapascal, 500 kilonewton meters, and the capacity of this one, let's say MUO is 600 kilonewton meters. So 5 MUO with the concrete only is greater than your M star. I'm okay. The beam will not gonna fail because it has enough strength. I don't need Rio. Then the standard plays smart again, saying that, okay guys, I understand your design, saying that your capacity and strengths are good enough, but what happens if it is snap break, that it just break without warning, it just fall down, the whole building collapse? Then someone said, ooh, that I don't know, I just make it that it is strong enough, saying that, okay. So let me tell you something, say that, okay, you put minimum Rio, that if I want to calculate this minimum Rio AST over BD, let's say equal to 0.02. So 0.002 B is 450 times by how much was that? 710, I believe. So you calculate that one. That is saying that 0.02 times by 450 times by 710. You put 639, let's say 640 millimeter square. Regardless of your design, you need, let me 640 meaning around here 902, let's say. Regardless of, because 640 will not here. So regardless of your design, you have N24 bar, you need to put 2 bars. Standard say, if you like it or don't like it, you need to put 2 bars. You need to put these 2 bars here. You need to put these 2 bars here. That will satisfy the minimum reinforcement required. Well, then should be okay. Okay, so 640. So that's what it means, minimum Rio. How much maximum Rio you can put? The maximum Rio you can put is P maximum. By the way, this equation is not given in the standard, so is based on our Ku value, gamma fc dash over fsy. So you can just put these all the values. I think you familiar with all these values right now, that where I'm taking those values. So the maximum Rio you get is 0.02. So let's check that P minimum, which is the Rio, is 0.02 from the standard. Then your Rio in our beam is 0.001. That is your actual Rio in your beam, and then you will have maximum Rio. P maximum is 0.02. Yeah, so that sounds good. This is less, this is less, this is more, and I'm in between, so that is okay. The reinforcement requirement is okay. We can also uh, then if it is everything is okay, we can calculate the moment capacity. If everything is okay, we can calculate the moment capacity. And I can like to add one more things here, that that you know the moment capacity, right? Okay, so the moment capacity would be, let's say, MUO equal to, you have tension force times D, take away the concrete force times DSC, take away this force times DSC. So where is coming from? If you remember this diagram, that you have this top Rio, you have this bottom Rio. I'm just putting the numbers, okay? Don't judge me that one. So CS, CC, and T. So if you, let's say, take the moment here at the top, then you have this D, you have this this DC, and you have this DSC, right? So that is all the parameters. Now we don't have this DC because we did not work it out, that DC one, which is 1/2 gamma DN, and now everything we have 0.89, and the DN value was 192. So you get that one is 86 millimeters. So we have all the values. The force is 2712 kilonewtons times by the depth is 0.71 meters. Concrete is 1977 times by this 86, so which is 0.086 meters. Take away this stress, 735 kilonewtons, times by this DSC was 0.062 meters. So if you just work it out, that one, you will get 1711 kilonewton meters MUO. And someone wants to add the capacity, you can have 0.85 times 1711 kilonewtons meters. So you just have a 1711 times 0.85. So you get 1454 kilonewton meters. So I hope you understand that 5 MUO is within the two examples, same kind, to demonstrate that that capacities. So I hope you understand. We have taken 3 examples total in the reinforced concrete, doubly reinforced.